with the physics tutor here. We are now going to deal with the Schrodinger equations. But in this first video, I'm going to first introduce the wave function, which we shall be using in the next videos for the deriving the Schrodinger equations, either the time-dependent and the time-dependent Schrodinger equation. So today's video, I'm going to only show you the wave function which we shall be using, the wave function of the particle. So we shall be using the principles, the postulates of the de Broglie, with the Broglie, yes, where he has the formula for the Broglie wavelength is equal to h over p. And we shall also use the Einstein's equation, where the energy is equal to h times f, meaning that f is equal to E over h. Okay? Yes. Now, the wave function of a particle which is symbolized as psi x is the one I'm going to derive, but it is a function of the position and the time. Okay? This is what I wanted to be shown. So we start by the psi x and t, which is equal to a times z minus r of omega t minus kx. So remember, omega is equal to 2 pi frequency, and then the wave number is equal to 2 pi of a wavelength. So this time we are using we are applying the Broglie wavelength, and this f is equal to energy over Planck's constant. So this one is equal to 2 pi times energy over Planck's constant, and then this one is equal to 2 pi times this, where the Broglie wavelength is equal to h over p. So this one is equal to 2 p over h. Now, remember, this Planck's constant is equal to the reduced Planck's constant is equal to the Planck's constant over 2 pi. This means that this implies that it is equivalent to writing that the Planck's constant is equal to 2 pi times this Planck's constant. So if we can replace the h with its value in this equation now, I will have that psi as function of x and t is equal to h times e minus r, and then I will have omega is equal to 2 pi e over h, then a t, yes, minus k is equal to 2 pi t over h times x, and then I'm going to replace h with its value here. It will be equal to this one is equal to a e minus r, then 2 pi e times t. Then the Planck's constant is equal to 2 pi times this Planck's constant minus 2 pi p x over 2 pi. I mean, h is equal to 2 pi times this Planck's constant. So this one and this one can cancel out, then this one can also cancel out, and then psi is equal to a e minus r et over this one as constant minus px over this one as constant, and then I can factor out one over this part as constant, or I can put it in fs. Then this one will give me that the wave function as a function of x and t, position and time, is equal to a times e over minus r, and then I factor out one over this part as constant. Then it will be over this part as constant. Then as a factor of t minus px. So finally, the wave function is given as a e over r over this part as constant of et minus px. So this one is the wave function. This one is the wave function that describes the movement, the motion of a particle in what we call the wave. In the motion of the particle as a wave. So now, this is the one we shall be using as we are deriving this Schrodinger equation in the next videos in time-dependent and time-independent Schrodinger equation. Thank you for watching. See you in the next videos while it is deriving the Schrodinger equation. Thank you for watching.